Okay, everyone. Our next speaker is the host and producer of the Applied Science channel on YouTube, which has released over 250 videos since 2011. His talk today provides an overview of laboratory techniques that can measure ultra-low concentrations. Please welcome to the Hackaday Supercon stage, Ben Krasnow.
Thanks very much. It's really good to be back in person. And it's actually relevant to the talk that I'm going to give you today. Soon after the last Supercon in person, I had a bit of a change in my career. So I've spent the last couple of years not doing hardware engineering, which is my background, but doing chemical sensing. So looking at really low concentrations of chemicals and using this information to build useful stuff. So it's kind of engineering, but chemical sensing. And so I divided the talk. This is going to be kind of like the sampler platter of all the most interesting things that I've found in entering this space of chemical engineering or chemical analysis. And I think that sometimes it's interesting to get a talk from someone in my position because I haven't been studying this for 10 or 20 or 30 years. And so all the stuff that was difficult for me to learn is fresh in my mind, or the stuff that was interesting and or difficult to learn is still fresh in my mind, and that's how I put together this sampler platter. So the talk has basically three parts. One's an important thing that you should take away and use in your daily engineering life. And then two example cases done expensively and cheaply. And we'll kind of step through all these things in sequence. So here's kind of a sneak preview here. We'll talk about why units are important. The first example will be lead in drinking water and wine. And then we're going to talk about volatile organic compounds and spelling disease and how to build your own detector. So I like this crowd because when we talk about familiar masses, I can put up an 0201 SMD resistor, and you probably know how big that is. As it turns out, it's about 130 grams, and that's going to be by far the biggest thing we're going to talk about in this whole presentation. So micrograms are where we start out, and femto or picograms are where we're going to end up by the end of the talk. So this is starting off on the big side. Just to keep a good visual reference of how big or small we're talking about. Throughout this talk, I've tried to add stuff that is that you can see with your eye or sense with your other senses. I can put up, a microscopic picture. You can see a single atom, but it's not very tangible. So I've always tried to include stuff that shows how big it really is. So the question is, can you see stuff smaller than this? Like, how small of a thing can you actually see with the naked eye? Can you see a nanogram? Yes, actually, you can. The way that I can show you this is by dissolving salt into water and then diluting that down to a really low concentration and then evaporating the drops on a glass slide. And with the right lighting, you can see really, really tiny masses. So we're starting off at 12.5 micrograms on the left, and we're getting all the way down to, quote, 0 on the right. Even my best deionized water that I have still has some contaminants in there. So 0 even has something there. You can see a smudge, but the 1.25 nanograms, it distinctly has more going on. So you actually can see a nanogram with your eye. It's not too hard. Let's talk about units a little bit. Can you see that? Almost. Some of you can see that, right? Okay, so that is 1 part per million. If this is the 1080p screen, and it's pixel perfect, that'll be 2 pixels. So 2 out of the 2 million pixels on the screen is 1 part per billion. You can actually see 1 ppm. It's actually a relatively high concentration. And again, if we're starting this talk off at like the thick end, 1 ppm is by far the most concentrated thing we're going to talk about in this whole talk. So you can see it with your eye. You can see micrograms and nanograms. Those are actually relatively easy things to detect. And here's where the important part of the talk comes in. So if you take away one thing from this talk, be careful with this parts per notation. So everything on this screen that I'm going to show you is 1 part per million. It's powerful. It's a very good way to describe things because it's so generalizable. You could be talking about, microhertz per hertz, or millihertz per megahertz, or milligrams per kilogram, or whatever you have. You can apply it to any unit because it's dimensionless. But that is also its pitfall. And we'll see how this gets really confusing and really important fast. So starting with the top left there, the most common way that you'll see a part per million. What is a part per million? If a scientist tells you it's 1 ppm, they usually mean it's mass per mass. So a milligram per kilogram. Easy enough. But if you buy like a water test kit, like for your aquarium or you're testing river water, a lot of times they'll say that a milligram per kilogram, or 1 ppm, is the same as a milligram per liter. Well, that's true for water only, because 1 liter of water is 1 kilogram at standard conditions. But it's very dangerous to say this because now this is not dimensionally correct. A milligram per liter is not unitless. It has units now, and it's not really 1 ppm. And the danger becomes when you think it's a milligram per liter and you switch to a different substance like air or ethanol or something else, you can get yourself into really big trouble. And then at the bottom there, occasionally it could also mean volume per volume. Microliter per liter is also 1 ppm, and now it's dimensionally correct, but it's equally confusing because you don't know if the person saying it means mass per mass or volume per volume. How many times have you bought like epoxy and it says mix it 4 to 1? Well, 4 to 1 what? Pounds per pound or liters per liter or whatever. You have to specify it. It's way too ambiguous. And now it's going to get much worse. In gases, remember, these are all 1 part per million. In gases, it's much more common to talk volume per volume. So a cubic centimeter per cubic meter is 1 part per million. But it's also common in the field to say milligrams per cubic meter. And now you have to know the molecular mass of the substance you're talking about, because in a gas, all of the particles are bouncing around. It's an ideal gas, but now you have to take into account the weight of the particles. So there's this conversion formula that takes that into account. And really, this ends up causing a huge amount of confusion. And if you think that I'm sort of overplaying this, surely people in industry don't make mistakes because they know what they're doing, right? I kid you not, this is actually a matter of life and death. A couple of years ago, this airplane took off from Gatwick Airport and had an engine surge just a few seconds after takeoff. A surge means that the jet engine no longer has flow going through it in such a way that it produces thrust. You've basically lost thrust from that engine entirely. So the pilots call Mayday, Mayday. Luckily, they still have the other engine going, and they're gaining altitude and turning around and trying to get back to the airport quickly when the second engine also dies. Now they have no engines. But luckily, they had enough altitude to cruise back to the airport, and we can laugh about it now because there were no injuries. Even the plane was okay after it got cleaned up. So what happened? There's this biocide treatment that's very common in the aircraft industry. I didn't know about this, but it's apparently having fungus growing in your fuel tanks is a big problem. And so they sell this fuel additive that you're supposed to put in your tanks, and the manufacturer says, put it in at 100 ppm. That's the entire set of instructions. And so you can kind of imagine where this is going. The accident report, and I'll read it, Base Engineer 1 was not familiar with the term ppm, ... So he searched the internet. He found a ppm converter and just typed in, what is 100 ppm? And who knows what he found or searched or found out, but nonetheless, he put in way too much of this fuel additive, and it basically clogged the engines upon takeoff because the plane tilted back and this very thick sort of, additive, ran back into the tank and got sucked into the engines and stalled the plane. So the only reason I even know about this is because someone made a YouTube video about it, and the person who put the video together made the same mistake that the engineer did in messing up the numbers. And someone in the comments pointed this out, who then also made a mistake about the numbers. So you got to be careful with these ppms. It's really just a disaster scenario. So if the company that made this biocide treatment just said you have to add it at 1 milligram per kilogram or 100 milligrams per kilogram, 100 ppm, there would be no mistake. And we're very lucky, actually, this plane was able to get back to the airport. So again, the one thing you should take away from the talk, always use units unless you really feel like you don't have to. The best place to use parts per million or parts per billion is when you're just sort of talking about orders of magnitude. Just give me a sense. Is it millions or billions or trillions, or what are we talking? But if you're giving actual instructions about how to mix something or how to measure something, just throw the units in there. It's very easy. Milligrams per kilogram. No confusion. I like this slide a lot too. Since we're talking about these orders of magnitude, in my daily work, it's very common to just sort of throw these things around where it's like, oh yeah, it was 15 parts per billion or whatever, or now we're to trillions. But these are like, we're crossing a lot of orders of magnitude. And so it kind of dawned on me that a human could count 1,000,000 seconds. It would be painful. I mean, you'd have to take breaks, but you could get it done over a reasonable period of time. It would take you a total of 12 days of counting. But you know, you could spread it out over a month. You could still get it done. But counting 1,000,000,000 seconds is probably beyond the realm, even though it's still technically possible. It's 380 months of straight counting. And with breaks, you know, you might be able to get it done. But 1,000,000,000,000 seconds is 32,000 years. It's just impossible for any human to count so many lifetimes. And so as we're going through this, it's good to keep in mind that crossing these layers between millions and billions and trillions is where things really get difficult. And there's an interesting parallel. As I said, parts per million are actually pretty high. You can see them with your eye. Similarly, measuring parts per million is no problem at all. Parts per billion, difficult. Parts per trillion, really difficult. The same sort of thing applies. And by the time you get to a drop of water, it's one with, you know, a lot of zeros there. And we're going to talk about counting molecules when we finish up this presentation. Okay, good. So let's talk about the first example here. Lead in drinking water. The EPA says, and they saw my presentation, so they actually say milligrams per liter instead of parts per billion there. 0.015 milligrams per liter is the action level, as they call it. So lead is one of these compounds that does the body no good. The ideal level is 0. But 0 is not an engineering quantity. So if you found 1 atom of lead in the entire drinking system of LA, that would be more than 0. So the EPA can't say that the limit is 0 because you could always find 1 or 2 atoms of lead somewhere. So the limit they've come up with is 15 micrograms per liter is the action level. That means you can take action if you measure your water and you have more than that amount in there. But as we saw, this actually is kind of a lot of lead. So you remember those little droplets that we evaporated, you can see 12.5 micrograms. That was actually the biggest water stain that we had on the glass slide. So just imagine you're sitting down at your table, you've got your little 12.5 micrograms of solid lead and your liter of water there, and you down the lead and then chase it with the water. The EPA says that is acceptable. And you can do it every day for your entire life, and that is actually an acceptable level of lead. And if you think that sounds like a lot, if you're an average person, you have about 8 micrograms per liter of lead flowing through your body right now. It's kind of shocking. And even funnier, the blood reference level, which is basically like the limit that doctors establish between normal people and people that should have something done, you know, require some kind of medical service, is 35 micrograms per liter. So it's actually quite a lot of lead before there's, you know, a problem, basically. But you have to measure all these levels. I mean, if you don't really know if you're over the line of 35 or not, how do you know if you really have a problem? So let's talk about the most common way that lead in drinking water is measured. This is a graphite furnace atomic absorption spectrometer. Quite a mouthful, but it is actually a relatively simple device in concept. Like everything, you know, you can say anything is simple in concept. Going to the moon is, you know, you take off and then you land. But it's in the details is where it gets troubling. So let's start with the easy takeoff and land description of how this works. You basically have a light and a graphite tube and a detector on the other side of the tube. That's it. That's the whole machine. You put your sample in the graphite tube and it gets really hot, like white hot, vaporizes everything that's inside there. And the little cloud of vapor will absorb some of the light and it will be darker at the detector than where it started out. That's the whole concept. And the cloud absorbs light and you can tell how much stuff was in your cloud by how dark the light is on the other side. But there's a couple of really interesting tricks of how this thing works. The light source is not just like a white light, tungsten, you know, source of light or anything. The light is a lead lamp. Like you've heard of neon lamps and maybe sodium vapor lamps. Well, this is a lead lamp. And so the light lines that come out of it, the spectral lines that come out of it, are characteristic of lead. And then if there's any lead in this cloud of vapor that's in this hot graphite tube, it will absorb at exactly those same spectral lines. So if you measure it on the other side of the tube, if there's any lead in your cloud there, it will absorb at exactly those spectral lines, and you can detect if there's any lead in there just based on the fact that the cloud has the same exact substance as your lamp. And if you wanted to test something like copper or something else, you'd use a copper lamp. And so these machines have like a turret of little, metal lamps, lead, copper, zinc, whatever you want, and you just rotate that lamp in and shine the special light through. And these machines can detect down to about 0.5 microgram per liter. Pretty good. As it turns, and so 0.5 microgram per liter, if you were able to dump a whole liter into this machine, that might be great. You could access all 0.5 microgram of that. But really, the way the machine works with this hot graphite tube, you have to vaporize your whole sample, and you can't vaporize a liter of liquid dumping in here. So typically what you do is put in 20 microliters, just a little bit shy of an eyedropper drop, into this graphite tube. And unfortunately, at 0.5 microgram per liter, this little droplet you're putting in there is only about 20 microliters. And so that only has about 10 picograms of lead that are actually going into the graphite tube. And that turns out to be about 30 billion atoms. So I was telling someone, I work with these machines now, or not this one in particular, but some that we'll see later in the presentation. And I was telling someone, we can detect down to, a couple picograms. I mean, a picogram is like a couple billion atoms. This is amazing. And they said, oh, is that a lot? No, it's tiny. If you're ever talking about atoms in sort of millions or billions terms, you're getting down to an extremely low level. So it's impressive that this little cloud of vapor works so well at absorbing light that you can detect this tiny, tiny threshold. There's one other really cool trick I wanted to talk about with this machine. You can imagine that if you vaporize this little cloud of atoms in there and you're doing this light absorption trick, there's all kinds of other things that are going to interfere with you. Water vapor, dust, you're burning this stuff at white hot temperatures, so there's gonna be smoke and stuff in there. How do you know if the cloud is absorbing like all wavelengths of light, like a soot cloud, versus just lead atoms that have been vaporized absorbing at these characteristic lines? I bet some of you know. A very clever way to do this is to put the whole graphite tube into a giant magnet. And when the magnet is on, the spectral lines actually shift a little bit due to the Zeeman effect. And so you turn the magnet on and you check how much light is going through, and then you turn the magnet off and check how much light is going through, and the delta is exactly what is due to this lead vapor absorption. It's a very, very good way of doing background correction. And I was going to do a video of basically describing this whole thing, and I still will at some point. But I actually became more interested in measuring the lead itself, and I wanted to come up with an easier technique that was cheaper and sort of just more accessible. So before these expensive spectrometers were common, I looked around for how lead was measured, professionally, and they used this chemical, which when I first found out about it, I thought it was pronounced, dithazone. It sounds like a psychoactive drug or something, but it's actually a very old substance that just forms very colorful compounds when it mixes with a metal. So each of the metals shown there, zinc, lead, copper, cadmium, mercury, gold, each of them has like a characteristic color. So if you have an unknown mixture of stuff, you can put dithazone or dithiazone in there, and judging from the color, you can tell what metals you have. And the intensity of the color is what is the concentration. So this is a pretty powerful method. The only problem is that if you do have a mixture, it's very hard to pick out exactly, because the colors mix together, and now you have to decode this like mess of color, which gets to be a pretty big challenge. So traditionally, here's the US EPA dithiazone method. You have to mix your sample with cyanide in addition to a bunch of other things. And the cyanide sort of removes all the metals that you don't want to measure, and lead is the only thing that's left. And then you measure how much light is being absorbed by this lead. So I thought, okay, that's a good method. I should do that. And I'll show you why I was so interested in lead in liquids in just a second, but this is my method. And so I was trying to come up with something that didn't involve the cyanide, just because I'd rather not buy that. And I also wanted to come up with a method that you could use potentially without bothering with the cyanide. So I kind of experimented with my own chemicals and came up with this method where if you're only measuring pure lead contamination, there's no other metals that are really contaminating your solution, you can mix these things together and come up with a really good calibration curve. One trick is that dithiazone is not water soluble, so you have to either mix your sample with alcohol or something, or I ended up using Triton X, which is it's a surfactant that helps the dithiazone mix into the water. And then what you do is you just put your sample with the dithiazone mixture with the surfactant in there and then do a spectrometer read. And this time you don't have to use the crazy lead lamp or anything, just plain old tungsten lamp shining through the vial. And you hook it up to your spectrometer and you measure how much is getting through there. And if you know there's only lead or mostly lead in your sample, the darkness of the color you can see there corresponds to how much lead was in the sample. Pretty straightforward. And here's what the curves look like on the spectrometer. Now, typically this method was meant to measure things in the part per million range. And I thought, well, let's give it a try. And things get a little bit weird down at the microgram per liter range, but I did actually get a pretty good calibration curve. So on the right there, you can see I mixed up stock solutions of lead, purposefully spiked with different amounts of lead, and ran it through the spectrometer. And you can see the progression from 0 all the way up to 1,000 micrograms per liter on the right there. So now we have like a calibrated working solution where we know if there isn't contamination from other metals, we can measure down to super low levels of lead. I mean, we're measuring, you can see the difference between 10 and 0 micrograms per liter. That's as good as one of these big fancy spectrometers can do. So this actually is a very good method if you're careful and you know that there's not other sources of contamination. So the reason that I got interested in this is because one of these myths out there is if you drink out of lead crystal, you'll poison yourself. Again, it's all a question about concentration. If you drink out of a lead crystal glass, yeah, you're going to ingest some lead. Is it 10 atoms or is it 10 milligrams? We don't know. And so if you search around on the internet, you'll find stories that basically talk about this in every way possible, where one sip will kill you versus you could drink out of the stuff every day and you'll be fine. And it's actually the older papers that actually have real information, like actual numbers about how much lead you'll be ingesting. One of the challenges with these things is that it's sort of a value judgment, like it's a risk profile that is something that people judge. So if someone asked you, is it okay to drink out of lead glassware? Well, some people would say it's fine and some people would say it isn't, but the thing that doesn't change is how much lead you're actually ingesting, and then you can decide if you have enough information, if that's actually a good trade-off or not. But I'll sum up by saying it matters a lot of how long the stuff stays in the glass. So if you pour some wine into a lead glass or a lead crystal glass, and drink it within 30 minutes or an hour, your intake is not going to be that significant. You could do that pretty much every day. It's not going to have a huge impact. But don't buy a crystal decanter and pour port in there and leave it on your shelf for 4 months. Don't do that. That is too much. And so these folks measured, you'll actually be ingesting about 3 or 4 milligrams per liter if you let it sit in there. And what's happening is the wine especially is very acidic, and it dissolves the lead out of the glass, and it just keeps pulling more and more lead into the liquid, and you'll actually end up with really high concentrations. This research paper is kind of funny because you could tell from the way they worded it, they were just sort of pulling bottles out of their own cupboard. And so they said, well, one sample had as high as 21,000 micrograms per liter, and that was brandy that was been sitting in there for, quote, a long time or something like that. So I'm going to do a video on this eventually too, but the short of it is it's okay to drink out of lead crystal glassware most likely, but don't leave it in there in a decanter. Okay, let's change gears a little bit here. We've been talking about micrograms per liter, which is smaller than ppm, but now we're going to go much lower even. I've spent most of my time looking at these volatile organic compounds, and the amount of undiscovered territory in this whole field is really mind-blowing. So just a couple years ago, this story was run on the BBC about a woman who could smell Parkinson's disease. It sounds totally off the wall. This was a really chance encounter that humanity sort of got for free. No one sort of guessed that this could work. This was something that just happened that is going to help us out a lot. It's kind of a funny story. This woman thought her husband smelled weird. Not too unusual, I guess, but she told, it took a few sort of chance encounters again that she connected the smell to the fact that he was recently diagnosed with Parkinson's. And she tried to get a couple of researchers interested in this and said, I think my husband smells weird because of his Parkinson's. And you can imagine the researchers', response to this. But she eventually convinced someone who thought she might have something to it and enrolled her in a blind trial. So what they did is they had about 20 or 30 people wear t-shirts, and then they gave her the t-shirts, and she was able to pick out who had Parkinson's and who didn't with 95% accuracy just from smelling the t-shirts. And the one person she got wrong later developed Parkinson's. And so it's a big signal. And like I say, the fact that we sort of got this thing for free, we, humanity, no doctors or scientists or engineers thought, well, I'll bet Parkinson's makes a smell and we better go find it. No, this was luck. This is just pure dumb luck. But the fact that we basically scratched the surface and got this amount of it already means that there's all these other applications where having the right detector with the right sensitivity means we can unlock all kinds of other things. And so, what was she actually smelling? Well, we don't know yet. Unfortunately, one of the challenges is that smell is a very complicated thing. There's not really like one compound that smells like X. Sometimes there is, but more often than not, there's like a bouquet of several compounds that interact with each other, and it's very complicated. So, of course, people have been trying to research this. Some researchers have taken samples from people with Parkinson's and sort of tried to subtract the samples from healthy people to see what this extra smell compound is. But it's very difficult because we're all exhaling like hundreds or thousands of VOCs right now. If we took a sample of the air in here, it's going to be completely loaded with everything, many, many, many thousands of compounds. And to say which ones of those specific ones are the Parkinson's compounds is really quite difficult. So let's talk about the equipment that they would use to find these things. Like, let's say you really were dedicated to try to find what this magic Parkinson's smell compound is. What kind of machine do you use? The gold standard is GCMS, and so probably everyone has heard of GCMS, but it's this kind of black box. And so I just want to give a really quick description of what this is and why it's not used more commonly. It's sort of the gold standard when you want to do chemical analysis, but it's also ridiculously expensive. It's like $500,000 plus for a full GCMS state of the art. And then you have to pay a technician to use it, and the sampling is very difficult. It's just not a very friendly piece of equipment. And I'll talk about first what GC is. When I say it's a GCMS, it's actually two separate machines that are connected together. So the sample goes through the GC, the gas chromatograph, and gets separated. And then those separated compounds go into the mass spectrometer, which functions kind of like a detector. A lot of the separation work is done by the gas chromatograph. And it's really the mass spectrometer that is doing the detecting of the stuff that's coming out of it. So maybe you've seen this, this great science experiment as a kid where you can sort of use a marker and draw on a piece of paper and then dip the paper down into, alcohol. And as the alcohol wicks up through the paper, it separates out all the compounds. Or if the dye is made of like several different colors, it will separate those colors out. And this is actually where the word chromatography comes from. It's basically separating out into colors. And for some reason, the name stuck, but we call everything chromatography now as long as you're separating compounds based on their ability to stick in a solid phase. So in this paper chromatography, the solid phase is the paper, and the different colors of the dye that are being separated there have different affinities for sticking to the paper. But this also works in the gas phase, and so a gas chromatograph is basically just a tube with a special coating on the inside, and you blow your sample through there, and just through the magic of diffusion and chemical affinity, the mixture will separate itself just as it goes through the tube. And you can kind of see the animation, how it works there. it's so simple, it's almost hard to understand, but it's just one compound moves through the tube more slowly than the others, and you end up with this beautiful separation without really doing anything. There's no moving parts, there's no really, the only difficult part is figuring out what the chemical composition of that tube coating should be. So that's a little bit tricky, but it's not too bad. And this works all the way down to, part per trillion levels. You can put a mixture of compounds in there where one compound might be 100,000 times more represented by another, and when they come out the end of the tube, it perfectly separates them. So you can detect things with a contrast ratio of billions to one even, if your detector is able to do that. So let's talk about the mass spectrometer. This is another one that, there's lots of different kinds of mass spectrometers, so I'm just going to kind of, give the overview here. But the idea is that you break your molecules up into fragments and ionize them so that they're charged, and then you can move the charge around and either measure how long it takes to move the charge through a period of space in your thing that's like a time of flight system, or you can make like a mass filter that sort of only allows one type of mass through. But the point is, I really just wanted to say that the limit of detection here is around 1 picogram, which is like 10 billion molecules. It really is the most sensitive detector that we have. Unfortunately, it's $500,000, and so that is a bit of a bummer. But it is still the gold standard, and no one has come up with something that's as versatile or sensitive as a mass spectrometer. But some of the work that I've been doing, in fact, most of the work that I've been doing recently, is to figure out how to make this cheaper. Like part of the problem, with this Parkinsons smell, the only reason that people didn't really think of doing that as sort of a let's just try it experiment is because this is so expensive and difficult to use. If you had a tool that worked almost as well as a mass spectrometer on your desk at home, think of all the different experiments people could be running just because it's so easy. You could be finding out all kinds of things, this uses in agriculture, uses in environmental testing, uses in health. I mean, the applications are really pretty endless. And the only reason we aren't doing those experiments is because these pieces of lab equipment are so expensive and difficult to get a hold of. So we got to make it cheaper and easier. And there's been some work in this direction. So an alternative to mass spectrometry is ion mobility spectrometry. The name is longer, but the cost is lower, and the complexity is lower too. So Mike's Electric Stuff did a great teardown. You've probably actually seen an ion mobility spectrometer and not known it. When you go to the airport and they swab your stuff to see if you're carrying on, bombs or, I can say onto the airplane, they'll put your swab into this machine and it will vaporize it and send it through an IMS. And again, the reason that it's an IMS and not a mass spectrometer is because it has to be cheap enough and small enough and easy enough to use to be used in an airport. They have to do the testing on site. So out of necessity, they had to use something smaller and cheaper than a mass spec. This is still a relatively expensive piece of equipment. Those things in airports are tens of thousands, but that's still a lot better than 500,000 for a lab grade MS. And the detection sensitivity is quite good. It's about 20 picograms for a typical IMS. And we'll talk about how they work. It's very similar to a mass spec, but you just let the air in. That's it. That's the whole thing. So it's basically a time of flight mass spectrometer, but instead of vacuum, you just have air inside it. That's the whole secret. Now, I know it sounds funny, but it does work. So when you talk to people who are familiar with mass spec, and you're like, well, you just turn the vacuum off, and you run your sample through. It actually works. I mean, you change the geometry and you change the electrodes a little bit, but it's the same thing. You basically ionize your sample, so once it's charged, you can move those molecules around with electric fields, and then you just see how long it takes to drag them through the air. And the bigger molecules will take longer to get pulled through the air by your field. Now, the travel times are a lot longer than in mass spectrometry. So in vacuum, your travel time might be measured in microseconds. And in air, since air is dense and you're kind of yanking these molecules through the air, the travel times can be more like milliseconds. So it, again, makes your whole system cheaper and easier because now you can just use a microcontroller to do the timing. It's not really that critical. You're only measuring tens of microseconds as your resolution, or even single-digit microseconds. And the other benefit of this is that you don't break up your molecules. For those of you that have used equipment like this, a mass spec typically fragments the molecule into all kinds of small little pieces, and then you have to sort of use intuition and previous knowledge about how things are fragmented to figure out what you had. But in air, you don't ionize them that aggressively. You keep the molecule whole, and then you pull it through air, measure the travel time, and you can figure out what you had. And the best thing about this is how you detect it. You just have a metal plate, so you're dragging your molecules through the air, and what happens when they get to the end? You just have a metal plate, and when the molecule hits it, you get one fundamental charge. And you just connect that plate to a transimpedance amplifier, and that's your signal. That's the whole detector, a metal plate and a transimpedance amplifier. And typical gains are about 100 million or even a billion. So a nanoamp becomes a volt, and bandwidths are typically around 30 or 40 kilohertz. And that's it. That's the whole analog business of this thing. And so it's actually linear. So I have down here in theory a 20 picogram burst. Like if you had a 20 picogram amount of sample that you put into this thing, that's about 200 billion molecules. That should generate about 38 nanocoulombs of charge if you just multiply it out. It's just one fundamental charge every time a molecule slams into there. And so in theory, that's 38 nanoamps over a second. But in reality, there's a ton of losses, an absolute ton of them. And so in practice, you really only get about 38 picoamps for a limited detection signal, which is about 20 picograms. But that's still pretty good. We're definitely in the range of something that can be smelled. So smell is very sensitive. Even dog smell is about part per trillion sensitivity. And these machines are absolutely in that realm, even on their own. But there's one last trick I want to show you that makes them even better. Oh, sorry, one other thing. So even cheaper, you can build one of these machines, open source even, and miniature for really low amounts of money. And these still have the same sensitivity. These are still 20 picograms sensitive. And they still have the same separation ability. So you can tell all the hundreds and thousands of compounds that you're exhaling right now can be identified by this tiny little open source, super cheap machine. And so kind of my pitch in this whole presentation is just that the more accessible and cheap lab equipment can be, the more experiments will run just because the equipment is available, and the more stuff we'll discover. If everyone had a mass spec, that would be great, but they really are just too expensive and difficult to use. A cheap detector, you wouldn't feel bad about taking it out to the pond and just sampling things, because if it breaks, it's maybe a few $100s. And this open source design is absolutely in that price range. Okay, now the last trick. Let's say you really do want to sense something that's even lower in concentration. So dog smell can get down to a part per trillion or 2 parts per trillion. And it's not quite, you need a little bit more sensitivity with your detector. There's this technique called thermal desorption. And it's basically just a tube of carbon, and you pull your sample through the tube, and all of the volatile organic compounds in there stick to the carbon particles. And so you can pull a large sample through there, many, many liters of air. And then after you're done sampling, you reverse the flow through the tube and raise the temperature so that all those volatile organic compounds now come out of the tube and go into your detector. And by using this, you can actually amplify the sensitivity of any detector you want by a factor of 1,000,000 pretty easily. So now you're sensing down in like the parts per quadrillion range, which is far below the smell threshold of any known creature as far as I know. Maybe certain things, but not really. And so if you really want to capture everything that's possible, if you put together thermal desorption, which is in itself is a pretty cheap technique. Remember, it's just a metal tube, carbon, and a heater. That's it. You extend the sort of sensitivity range of all these pieces of equipment even further. So I'll just leave you with the things. Remember, part per notation is a problem, and this extends to part per 100 notation, which is otherwise known as percent. You've got to be really careful with this like unitless notation. Avoid it unless you're just giving like ballpark references. Low concentration chemicals are important. If we can detect disease with smell, that is a dramatic improvement over the standard of care. And sensitive detectors can be really, really cheap. And the more of them that we have and the more people that have access to them, the more that we'll discover. And you should check out that DIY IMS project, or come find me in the back alley there, and I'll tell you all you want to know about IMS. So thanks very much.